Okay, let's do discussion 5.1. We're going to talk about changes in enthalpy. We're going to talk about experimentally measuring enthalpy changes, and we're also going to talk about theoretical calculations using average bond enthalpies. Okay, so when we talk about energy, there's lots and lots of forms of energy, but we're going to focus on kinetic and potential energy in chemistry. So two types of energy we're going to focus on. Kinetic energy is energy of motion. So as temperature increases and particles move more quickly, their kinetic energy increases. Potential energy is stored energy in chemical bonds. And energy can be converted between the two types, but can't be created or destroyed. So law of conservation of energy. Okay, so let's talk a little bit about heat. Heat is the measure of the total energy in a given amount of substance. Flows from a warmer object to a cooler object. So when a warmer object loses heat, its temperature decreases, the molecules will move more slowly. When the cooler object absorbs heat, its temperature will rise and the molecules will speed up. And the transfer of energy will continue until they reach thermal equilibrium and both objects have the same temperature. When we compare heat versus temperature, it's important to understand the difference because a lot of people do get these mixed up. So heat is a form of energy, whereas temperature is just a measure of the average kinetic energy of a substance. And really significantly, heat is extensive, so it depends on the amount of the substance, whereas temperature is intensive, so it doesn't matter how much we have. The easiest way to understand this is to think about boiling water. So if I have a pot of boiling water on the stove and a drop gets on my hand, it'll sting a little, but it won't really hurt. If I spill an entire pot of boiling water on my hand, that's going to hurt a lot. And that's because these have the same temperature, but we're talking about different amounts of heat. Enthalpy is the heat content of a system at constant pressure. So most processes, physical and chemical, involve a change in enthalpy that we can measure in a lab. So even something as simple as dissolving a salt in water usually involves a change in enthalpy. We measure this in joules or kilojoules, and remember that 1,000 joules is equal to 1 kilojoule. Now, we're not going to measure enthalpy directly. So if I have a system where nothing's changing, I can't just measure the enthalpy of that system, but we're looking at the heat that's added or lost. So we're looking at the change in enthalpy. So delta H. The standard enthalpy change of reaction is noted like this, and that just means that we have standard conditions. So it's occurring in a system where we have 1 mole of matter being transformed by a reaction, and the standard conditions would be 1 atmosphere pressure, 100 kilopascals, and 298 Kelvin. So it's a little different than STP when we talked about gas laws. A lot of these happen in aqueous solutions, and since standard temperature when we talk about gas laws is 273 Kelvin, that doesn't really make sense to use here because that's the freezing point of water. Okay, so let's look at a problem that involves standard enthalpy change. So the standard enthalpy change for combustion of octane is negative 5,741 kilojoules per mole. So that means that heat's being given off since we have a negative enthalpy. So we're going to calculate the amount of energy produced in kilojoules when 1 gram of octane is completely burned. The easiest way to do this is dimensional analysis. So if we have 1 gram of octane, we can convert that to moles, and since we know how many kilojoules are released per mole of octane, it's easy to solve for the moles, or for the kilojoules, given this particular amount. Let's talk about endo and exothermic reactions. We just talked about how the sign of the enthalpy of the combustion of octane was negative. That meant it was exothermic, giving off heat. So in a chemical reaction, energy is required to break bonds in the reactants, and energy is released when new bonds are formed. So depending on the amount of energy required to break the bonds involved and then that's released when the bonds are formed, there will be either a net positive change or a negative change. So we're just comparing the relative amounts, basically, of energy involved. And in an endothermic reaction, heat is absorbed from the surroundings. And that's because more energy is required to break the bonds in the reactants than is released when the bonds are formed in the products. So energy is flowing into the system. In an exothermic reaction, heat is given off to the surroundings. And that's because more energy is released when the products form than is required to break the bonds in the reactants. You should know that combustion and neutralization reactions are always exothermic. So reaction coordinates are a visual way that we can show endo and exothermic reactions. So in an endothermic reaction, remember that heat is entering the system. So the products have higher energy than the reactants. So we have enthalpy on the y-axis and the reaction pathway on the x-axis, and that's just a fancy way of saying this is what happens as the reaction proceeds. So we see that the products have more energy than the reactants. The change in enthalpy is positive, and energy is absorbed. The products are also less stable since they're at a higher energy, and lower energy is associated with greater stability. And we can use this for a lot. We can use this to calculate the activation energy of the forward reaction, shown as E sub A. We could also calculate the activation energy of the reverse reaction, although that isn't shown here. And we can calculate the difference in enthalpy by comparing the reactants and the products. So here, since the products have higher energy, delta H is positive. In an exothermic reaction, it's the opposite. The products have less energy than the reactants, so there's a net loss of energy from the system. Energy is released, and the products are more stable because they're lower energy. When we measure enthalpy change, we're going to use something called a calorimeter. So calorimetry is the measurement of heat absorbed or released in a reaction, and in order to do a calorimetry reaction, we have to make a few assumptions. The first assumption that we're making is that we're not losing any heat to the surroundings in the calorimeter, so it's perfectly insulated. It's not a really realistic assumption, but we have to make it in order to do these calculations. And so we're assuming that the energy gained or lost by the system is equal to the energy gained or lost by the surroundings. We're going to use a very familiar equation when we do calorimetry problems. We're going to use Q equals mc delta T, where Q is heat, M is mass, C is specific heat, and delta T is change in temperature. Final minus initial, or really when we're looking at temperature increases, we're looking for the maximum recorded temperature. If we were looking at something where the temperature is decreasing, we'd be looking for the minimum recorded temperature. Okay? So, specific heat capacity is the amount of heat per unit mass that's required to raise the temperature of a substance by 1 degree. You should know the specific heat of water. It's 4.184 joules per gram Kelvin or kilojoules per kilogram Kelvin. You're going to use it so much, though, that you really will probably have it memorized. Now, in order to find delta T and be as accurate as possible, we need the maximum possible temperature, but it can be really difficult to find this. If you think about it, if we're doing a reaction where we're mixing two things together, as soon as the temperature starts to rise, heat's being lost to the environment. So unless the reaction is completely instantaneous, we're not going to be able to get the theoretical highest temperature. All right, so we can use a graph to help us find what the theoretical maximum temperature would have been. Okay, so this is a graph that shows temperature over time, and you can see the moment at which we added the two reactants together, so just after 100 seconds, where the temperature starts to increase rapidly. Okay, and you see that it reaches a maximum and then decreases, and we have a constant rate of heat loss. Okay, so you see the point where the reactants are mixed, and that's the initial temperature of the reactants. Now, T1 is the highest recorded temperature that we actually reached. But we want to know what the theoretical highest temperature would have been if the reactants had had a complete and instantaneous reaction, so no heat lost to the environment. So we can extrapolate backwards. We're assuming the same rate of cooling. So if we extrapolate back to the initial moment the reactants were mixed, we can come up with a theoretical maximum temperature. So that's the temperature that would have been reached if there was no heat loss to the surroundings. Okay, so let's look at another specific heat problem. This gives us the specific heat of iron as well as the mass of a block of iron and a temperature change, and it wants us to calculate heat. So we're going to use Q equals mc delta T. Now when you're doing problems like this, you do have to be a little bit careful because you really have to keep an eye on your units. If you look at specific heat, it's given in joules per gram Kelvin, but we have kilograms here. So I would just go ahead for some, you could change that unit to make it kilograms, but I would just go ahead and convert my kilograms to grams, okay? Now you might be thinking that we have another units problem because we have degrees Celsius and Kelvin, but we don't actually have a problem here. If you were to convert both of those temperatures in degrees Celsius to Kelvin, you would add 273 to both of those numbers. So then when we subtracted them, we would get the same delta T. So when we're looking at delta T, we don't have to worry about converting from Celsius to Kelvin or vice versa. Okay, so when we solve this problem, we'll get 30,003.75 joules. That's what our calculator would tell us. Okay, but this is all experimental, so we want to really keep an eye on our significant digits. When we look back at the problem and the significant digits of all our measurements, our final answer should have 3 significant digits. So there's 2 ways you could do this, really. You could use scientific notation and say 3.00 times 10 to the 4th joules. If you wanted to, you could also say 30.0 kilojoules, and that would serve the same purpose. Okay, let's look at another problem. And problems like this can be a little overwhelming for students sometimes because there's a lot of numbers and it seems like there's a lot going on. So anytime you see a problem like this, it's helpful if you can just imagine doing this problem. Okay, so mixing 5 centimeters cubed of glycerin, which has a density of 1.261 grams per centimeter cubed, with 20 centimeters cubed of water in a calorimeter. We have the initial temperature for glycerin, which is 23 degrees Celsius. Initial temperature of water is 50 degrees Celsius. We have final temperature of the mixture, and we're trying to find the specific heat of glycerin. Okay, so we're going to assume that the calorimeter is perfectly insulated. So the heat that is lost by the water is equal to the heat gained by the glycerin. Okay, not all of the heat that the water is losing is being transferred to the glycerin, though, so there is some heat lost to the environment. Now, when we think about what's happening in the calorimeter, we just have these 2 things dissolving and heat transfer from the warm to the cool substance. So, we're assuming that the heat that the water lost is the same as the heat the glycerin gained. So we could say that Q glycerin is equal to negative Q water. All right, so likewise, we could say that MC delta T for the glycerin is equal to the negative MC delta T for the water, just by substituting. All right, so we're going to set up a 2-sided problem. We're going to keep glycerin in green and put water in blue, just to make it a little easier visually. Okay, so MC delta T equals negative MC delta T. Technically, it doesn't matter what side you put the negative sign on, because that's how algebra works, but I usually just put it on the side that is losing heat because it makes the negatives cancel out a little more neatly. Okay? Now, we're not actually given mass directly in this problem, but for glycerin we are given volume and density, so we can just multiply those to get the mass. We're not given the density for water, but you should know, and it's in the data booklet, that the density of water is 1 gram per centimeter cubed. So if I have 20 centimeters cubed of water, I have 20 grams of water. Okay? It's important to do the final minus the initial temperature. If you don't do that on the water side, because you'll get a negative when you do 45 minus 50, and that'll cancel out the negative there. Okay, so if you don't do that, you'll know, because you should never get a negative value for specific heat. That's not a thing. Okay, so then it's just algebra, simplify, and solve for the specific heat, and you get 3.0 joules per gram degree Celsius. Okay. Let's look at another problem that seems a little overwhelming, but actually isn't quite as complicated as it seems. All right, so let's imagine we're mixing 1 liter of 1 molar barium nitrate with 1 liter of 1 molar sodium sulfate. Okay, so basically we're mixing 1 mole of each of these at 25 degrees Celsius. We're just pouring a liter of this and a liter of that together, and we're forming a white solid barium sulfate, and we're noticing that the temperature of the mixture increases to 28.1 degrees Celsius. All right, so we're going to make the same assumptions we've been making. Calorimeter absorbs negligible quantity of heat, specific heat capacity of the solution. We're assuming that that's the same of water, as the heat capacity of the solution is the same as that of water, and we're going to make that assumption a lot. We're also going to assume that the density of the final solution is the same as that of water, 1 gram per centimeter cubed, and we're going to calculate the enthalpy change per mole of barium sulfate formed. Okay, so a couple things in this problem. First, let's figure out what's happening in the calorimeter. It's a precipitation reaction. Aqueous barium nitrate and sodium sulfate are going to form solid barium sulfate and aqueous sodium nitrate. This isn't balanced. You need a 2 in front of the sodium nitrate, but those are just spectators, and they're really not going to be relevant in our final calculations. Okay? Now, we can't directly measure the change in enthalpy of these substances. The water here is the medium where this is happening, and it's really the surroundings. So we can measure the heat that the water gains, and that's equivalent, well, it's opposite, of the heat that the system is losing. Okay, so because we're measuring the surroundings, and we usually are, delta H, the change in enthalpy of the system, is going to be equal to negative Q. Okay, because we're measuring the surroundings, but we want to know about the system. Okay, so first we're going to calculate Q, and then we're going to find the enthalpy change per mole of barium sulfate. Okay, so let's start by calculating Q. Now, we're going to use Q equals MC delta T, but this isn't quite as obvious as some of the other problems. All right, so we're talking about the whole solution. We know we're going to use the specific heat capacity of the solution as 4.18, and delta T is pretty easy because both of the initial solutions were at 25, and it went to 28.1. Mass is a little bit trickier. All right, so we poured 2 liters of this stuff together, right? Total of 2 liters, 1 liter of each. We're also assuming that the density is 1 gram per milliliter. So if we had 2 total liters of solution, that means 2,000 milliliters, so therefore 2,000 grams. Okay, and that 3 there should be a superscript. So we would get 25,916 joules. Now remember that delta H is negative Q. So delta H is going to be negative 25,916 joules. To take into account significant digits, we'll say negative 25,900 or negative 25.9. And then, and with those significant digits, I assumed that the density of the water was exact, so I didn't count that as limiting for significant digits. And when we find the enthalpy change per mole of barium sulfate, it might help to look back at our balanced equation from the slide before. Assuming there's a 2 in front of sodium nitrate, but again, we don't really need that. We had 1 mole of barium nitrate and 1 mole of sodium sulfate that produced 1 mole of barium sulfate. So we only produced 1 mole of barium sulfate, so we just have to divide by 1, and we get negative 25.9 kilojoules per mole. Okay, last part of this, we're going to talk about average bond enthalpies. And these are found in table 11 in the data booklet. So the average bond enthalpy is the amount of energy that is required to break a bond or that's released when the bond is formed. And the units are kilojoules per mole. So it's basically if we broke an entire mole of these bonds, how many kilojoules would be required. Remember, energy is released when bonds are formed and absorbed when they're broken. People are usually pretty okay with the idea that energy is required to break bonds, but it's a little harder for people to accept that energy is released when bonds are formed. Average bond enthalpies are obtained by considering a lot of similar compounds. So you know now, having studied organic chemistry, that carbon-hydrogen bonds are in a lot of different compounds. So what you're seeing here is an average, and we'll talk about the limitations of that in a little bit. So the general formula when you're calculating enthalpy using average bond enthalpies is that the enthalpy is the sum of the bonds broken minus the sum of the bonds formed. All right, so let's look at an example, the combustion of methane, and we're going to calculate the enthalpy using average bond enthalpies. Okay, so what bonds are broken? All right, well, we have to think about methane, so you're going to really need to draw these structures. Methane has 4 carbon-hydrogen bonds, so those are broken, and then their oxygen is, diatomic oxygen is an oxygen-oxygen double bond, and there's 2 of those. When we think about the bonds formed, carbon dioxide has 2 carbon-oxygen double bonds, and then each water molecule has 2 oxygen-hydrogen bonds, but there's 2 of them, so we have a total of 4. Okay, so sum of the bonds broken minus the bonds formed. Separate these out. Calculate the bonds broken together, the bonds formed together, and then subtract. You'd be amazed how easy it is to make a little mistake when you're just adding and subtracting, but it's very easy and people do it all the time. So really, really take your time here and be very methodical. Okay? You also need to make sure that you get the correct bond. So if it's an oxygen-oxygen double bond, make sure you don't use an oxygen-oxygen single bond. Okay? We'll collect our terms, and when we solve, we get negative 808 kilojoules per mole. This is a combustion reaction, so we would expect it to be exothermic, so it's good that we got a negative number. If you were calculating this and somehow wound up with a positive number, that should be sort of a red flag. Oh, hey, this is combustion. I know this is exothermic. Let me recalculate. I want to talk briefly about the limitations of this method. So in practice, we know that the energy of these bonds might vary slightly because it'll be a little bit different in different compounds because it can be affected by neighboring atoms. Like we said, there's carbon-hydrogen bonds in just so many different things, and they're all going to be a little bit different. So these enthalpy values that we get from average bond enthalpies may not necessarily be very accurate. There are a few exceptions where we actually have bond enthalpies that are precise and not average bond enthalpies. The diatomic halogens and hydrogen are great examples of these because the only time there's a bromine-bromine bond is in Br2, diatomic bromine. Okay? The same thing for hydrogen, and so these are going to be exact numbers. Okay? Not an average in this case, so those would be more accurate than something that's an average. And these are also in the gas phase. So using average bond enthalpies to calculate enthalpy would not be very effective if we have things that are liquid, solid, aqueous, etc. Okay, so pause for a second, practice this. You really need to draw these structures. So draw them first, figure out the bonds broken, bonds formed, and calculate. Okay, so let's look at the bonds broken and formed. So we have a nitrogen-nitrogen triple bond that's broken. This is why it's so important to draw these, because otherwise you might have just thought that was a single bond. And 3 hydrogen-hydrogen single bonds. Bonds that are formed, 6 nitrogen-hydrogen bonds. It would have helped to draw out ammonia, and I would recommend drawing it twice, because then it's easier to count and harder to make a mistake. Okay, and then you're just grabbing those values from the data booklet and solving, again, being very, very careful and methodical, and you would get negative 93 kilojoules per mole. Okay, try one more, and again, make sure you draw these out, especially propane, and account for every bond. Okay, broken. 2 carbon-carbon bonds. People often forget that. 8 carbon-hydrogen bonds and 5 oxygen-oxygen double bonds. Since we have 3 CO2 molecules, there's a total of 6 carbon-oxygen double bonds, and 4 waters means 8 oxygen-hydrogen single bonds. So we're going to put all these numbers together. We're going to be very, 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 very careful, and you should get negative 2,030 kilojoules per mole. And again, combustion, so it should be a negative result. Okay, do your homework, practice, ask questions, the end, yay!